Okay, one more problem here. It's a little bit of a different one. We have this weird looking mechanism crazy thing with a spring and a weight, and it's in the vertical direction, or it's in the vertical plane, I should say. And there's this weight of 400 pounds, and it's attached to this lever arm. And there's a spring right here that's a constant 250 pounds per inch. And the spring is when it's unstretched, that means that this theta is equal to 0, right? So if we were going to imagine what that would look like, I'm not sure what the weight is doing. The weight's just hanging right there kind of thing. But the spring is not like being the thing. So it like rotates over to here somewhere at some angle, and the spring is then stretched. So we want to figure out where equilibrium is. So basically, we're looking for a theta. And so this is, a little bit different because it's sort of like this generic kind of setup right here. So one thing that we could notice is that the length of the spring is actually going to be the length of this arc right here, the length of the stretch of the spring. And so we know that force is going to be equal to K times, and we'll just call it X. A lot of times, actually, I like to call it del right there. That's the stretch of the spring. The stretch of the spring is going to be an arc. Well, you could find an arc length by taking the radius and multiplying it by the angle as long as this is in radians. Right? So that's the purpose of the radian, really, right? 2 pi is 360 degrees. If you multiply that by the radius, you get the circumference, right? So anything that's like pi times the radius, you get the arc of a 180 degree half circle, right? You get the outside, the circumference, or the arc length, I should say. So anything that, radius times radians, or the angle in radians, is going to be the arc length. And so that's the radius right here, the arc length the thing is moved. So that's going to end up being that 250 times 3 times theta. And I'll just leave it that way for right now. And so now I'm going to draw my free body diagram. I could have done that right away. And we don't know the angle, so we can keep that as an unknown, or just make it a sort of a generic angle. As part of this, I will put the forces on here. So we got a 400-pound force, and we have a force coming this way, and that's the force. Let's call that the force of the spring. Force of the spring. We also we might have some reactions in here. Reactions this way, but there's no moment on here because this is free to move about this. If we had some dimensions that we're going to add onto this, we would know that this was R right to there. We would notice that this was the length of this thing, and then we would also notice this theta was taking place. And I forgot to declare my X and Y, although it doesn't matter. So what we do here is take the sum of the moments about O. Maybe I should call this O. Maybe I should have written out what the labeled the reactions. This is Roy, and this is Rox. And just that's a fully labeled FBD, even if we don't need it. And we say the sum of the moments about our O is going to be equal to 0, and we're going to take that as positive. So we take a look at this 400, and we're going to take 400 times this length right here, which was 8 inches, but that's going to be times the sine, right? Because that's the actual dimension right there that we would be going across, that dimension right here. And we know that that's the sine. I think my battery just is getting low right here. Uh-oh. Let's see what happens here. Previous? Yeah, okay. So let me go back to my extra battery backup here. right? Did it? Okay. And that's a little concerning. Let's see. Can I write this way? I can kind of write this way. It's a little hard to do this way. Okay, so that's 400 times 8 times the... Oh, I don't want that color. Let me switch colors. Sine of theta. And, okay, so that's going to be the counterclockwise, so that's positive. And now we take a look at the force of the spring, right? So that's going to be negative, that force of the spring, which we set up here, was 250 times 3 times theta. But then need a moment arm, right? That's just a force. So we also need to go times the radius, which we know is going to be 3 inches. If I work all of this out, I get, I didn't divide it all the way through, 3,200 times the sine of theta. I'll bring it on to the other side. It's going to be equal to 2,250 times theta. That's weird. What do I do now? Oh, that's a... I'm trying to remember the name of this kind of equation. I think it's transcendental. That might be incorrect. We could look that up in a second. But so how do I solve this? Well, the book says trial and error, and it doesn't tell you how you would do that. Well, you want to make sure that your calculator is in radians when we go to do this, or flip back and forth between here. But we might take a guess and take 45 degrees into the thing. And then, so we might take pi over 4 and stick them in there and then solve for theta and in radians. And if you get the wrong thing, then maybe you should, and it's too small, maybe then you add something to that 45, right? And then you trial and error until you get back and forth until you come up to, you can converge to a solution. But what I would choose to do is go to Wolfram alpha. So let me keep this right here. And so I go to the magic thing, which is Wolfram alpha. And how much did it say? I was only on 21% on my screen here. But let's see. I will go to my Wolfram. It probably knows it right here. Wolfram alpha. Wolfram alpha. Wolfram syndrome. I don't know what the heck that would be. But it's a nice thing right here. So I'll just type this thing in. Just type it in. 3,200 times sine theta is equal to 2,250 times theta. Right? Boom. It's going to do its little cranking thing and think. And it gave me, there's actually, what it's doing is doing a line through where this thing would have seen the intersection points. But we see that we get an answer of 1.402. But these are radians, right? So that angle is in radians. So how much is that? Then you start to ask, well, okay, so come back down to here. I guess I'll just use the numbers right here. So we were told that theta was approximately 1.4020, and these are radians. And do you remember how to switch into radians? So you go 1.402 radians, and the easiest way is to say that I have 180 degrees is divided by pi radians, right? And so now we turn it into degrees, and we get that it's going to be 80.33 degrees. So theta is, I guess, let's stick with the approximately 80.3 degrees. Boom. And if we go to the book, we see that we get the same answer, right? So that was one solution to it. So there we go. This is the sample problem 4.5. And the video is 10 minutes long.